And hello, welcome to this video. Without further ado, let's just start with our coding of the Ping-Robinson equation of state. Okay, I'll do it in Rust. And we already went through some of the Git things already. So I'm just going to run the cargo watch-x test. Now, of course, there'll be some warnings, but we can clear them up later. Okay, most important is to get this this cargo test going. Okay, we want to solve for the equation of state for volume. Okay, Ping-Robinson equation of state for volume. We did pressure last time. It seems to work nicely, and we actually did a test. Can't remember where the test was, but I think it's in main.rs. Yeah, here's your test. Right, it's here's where the test is, so you can actually run it to see whether it works. Okay, it should fulfill this criteria in order to work. So we've gone through that before. Now we want to talk about volume. So let's just do the volume bit. Yeah, this one's the get molar volume for Ping-Robinson equation of state. Okay, I'm going to do it live in front of you, so none of this is rehearsed. I might run into bugs along the way and get stuck along the way, but the whole idea is to show you, the programming process. Okay, so right, here we go. Yeah, first let's do the easy bit, right? You see here, this is the cubic polynomial we need to solve. Okay, so we are solving for the z term right here, z. So z cubed minus 1 minus b z squared, and then all of these terms are here. All of this should equal to 0. So the easy bits, okay, thankfully you don't have to write it out, and programming you can do a lot of copy and paste. So polynomials are usually not a problem. I'll just do b first. Okay, I'm gonna have let b equals to b times pressure divided by where's the molar gas constant? Yeah, molar gas. I'm gonna look for molar gas constant. Okay, here it is. Okay, I'm using Vim key binding, so don't mind me. You can actually use your mouse as well. But yeah, I'm just more used to this, right? It's really much more comfortable for me. So divide by molar gas constant and divided by the temperature, right? That is the B. Okay, so again, B is not used, and it's Rust is complaining that it should have a snake case name. So well, I'm going to try to conform to that. So I'll rather you call this capital B. Capital B. So it's this big B over here, but it at least Rust doesn't complain about it. So this is the B. And let's do capital A. Let capital A equals to what? Okay. Okay, let me close this first. Let's see what type capital B is. Capital B should be a ratio, hopefully. Because all this should be dimensionless, because Z is dimensionless here. So A should also be dimensionless. If you see here, A, B, and B squared, all of these are the same units. So A should also be ratio. So capital A. So this is ratio. By doing this, I am enforcing the type to be ratio. Otherwise, it will not compile. So I'm not using a Rust type inference. I am specifying the types as is. Okay, so it's AP over RT, right? AP over RT. AP over R squared T squared. Excuse me. So I don't have the A yet. I will need to find A first. So where do I find A? Okay, A is right here. So A of T is 0.45724 R squared TC squared over PC alpha T. So before we do anything, we also need the alpha T as well. So I'm going to do this I'm just going to have this let alpha. Okay, so this is alpha, and it will be sort of okay, there's a problem because I have not specified the type yet. The type inference will come later. Or maybe I will just, instead of doing everything, all of this, I'll get the reduced temperature first, because AT depends on alpha T. Alpha T depends on the reduced temperature and also on kappa. So let's do the kappa first. So okay, let kappa equals to get kappa. Okay, eccentricity factor. So I have my kappa. We've coded that before. So we use the kappa again. Let's get the reduced temperature. Okay, this is a ratio. This will be the temperature divided by critical temperature. Okay, that is the reduced temperature. Now that's done, I can just easily do the alpha T. So alpha equals to well, maybe I'll use square root alpha, since I don't want to, I want to keep my stuff a little bit neater. So this is 1 ratio. Wait, did I do this before? Square root. Yeah. Okay, I did this before. So I'm just going to copy and paste. I'll paste it here. Okay. And alright. Apparently there's a mistake here because yeah, I misspelled my reduced temperature in the other function. So let me just do a quick correction. Okay. TMPERATURE. Okay. Okay, so square root alpha is there. Then let alpha equals to square root alpha times square root alpha. Okay. So square root alpha is the stuff inside the bracket. Then I multiply, I square it, and then I'll get alpha. Once I get alpha, I can get AT. Right? So this one here seems to be the so-called numerator. This numerator, but I'll just call this alpha, or A. This is A in this case. So let's just check the numbers. 0.45724 times R squared, so molar gas constant times molar gas constant, times critical temperature divided by critical pressure times alpha. So this is the this is A. This is A. So this A of T is here. And then what is this capital A? Okay, capital A equals to A times pressure divided by molar gas constant. Okay, divide by molar gas constant times temperature times temperature. Okay, so A, this capital A. Oh, look. Oh, great. Looks like we have a problem. We have a slight problem here. The units seem to be wrong, so I think, yeah, we need to do something about that. So let's you have to check whether things are really, dimensionless. So let's go up. Okay, so we have alpha t. Alpha t should be dimensionless. Okay, alpha t should be dimensionless. So reduced temperature is a ratio. Square root alpha is a ratio. I think alpha should also be a ratio. Okay, whatever type A is, we'll have to figure it out later. Or we can just take a look here. R squared TC squared over PC. So R squared TC squared over PC. Okay. Let's see. Yeah, looks like there is some form of error down there. So Oh, right. See, yeah, that's the mistake. Okay, good. Good thing that the units of measure or UM create actually helps me to catch these bugs early, because there's a wrong unit there somewhere. So all of these here, these are okay. A is okay. We copy and pasted it before. It's tested code. But you can see, yeah, I made a mistake real time. Pressure should be in the numerator. The rest of the things should be in the denominator. So molar gas constant and molar gas constant should be in the denominator. And T square should also be in the denominator. So if you were paying attention and you caught the bug while I was typing things out, good for you. Okay, so now things are there, but this just goes to show the usefulness of the UOM package in case the units are wrong. Okay, so this is also why I choose to put the ratio type here, so that you know the ratios are there. Okay, the ratios are there, as in we expect capital A to be dimensionless or else a ratio. Capital B is also dimensionless or ratio. So by enforcing the type beforehand, okay, and not letting Rust infer the type, you're able to do this units comparison very easily, as you saw just now. Okay, next step will be to do our coefficients. So we have a few coefficients here. This is the 1 minus b. Okay, so I'm going to do 1 minus b, capital B, and this will be a ratio. Okay, so I actually want to copy and paste this whole thing here. So I'm going to copy and paste. I don't know how this will turn out. Okay, so z to the, okay, this did not turn out well. Okay, never mind. Let me do z cube plus, okay, minus 1 minus b, okay, z squared. So this is the equation we're writing out. So what we need to do is to, you know, well, I want to make it easy for people to see what I'm actually trying to do here. So I'm copying this equation, and then I'm actually defining terms right here, like 1 minus capital B. So 1 minus capital B is this term here, 1 minus capital B. A minus 3b squared minus 2b. Okay, so, and this is the z term. Okay, and the last one is minus ab minus b squared minus b cubed. Okay, so 1 minus capital B is quite easy. So ratio new ratio 1.0 minus b, or capital B. That's easy. So, next one is let capital A minus 3 cap, okay, B squared minus 2b, 2 cap B. Okay, so this is a ratio. I'm using a very long name, but I want to make it clear what ratios I'm actually trying to do. So this is a capital A minus 3.0 times capital B times capital B minus 2.0 times capital B. Okay, so this is it. Okay, so let's just check. Capital A minus 3 capital B squared minus 2 capital B. So capital A minus 3 capital B squared minus 2 capital B. So this is the term over here. Okay, last one is the let cap AB minus B cap B squared, okay, minus B cubed. Okay, this is also a ratio, and so I do capital A times capital B, all right, minus capital B times capital B minus, okay, I'm going to copy and paste this, and I'll do capital B cubed. Okay, so probably there is yes, there's a wrong thing here. This should be a capital R ratio, not a small r. There's a difference. Okay, so now we have this cubic polynomial. We can actually solve for z. All right, we can actually solve for z. Okay, how do we solve for z? We will need to do this bit here. Now the equation here is kind of quite long-winded. So actually there are a few options we can do. One is to code all of this in manually. And the second is to go to the crates IO and use the roots finding formulas there. Okay, one of those formulas is called not formulas. One of those crates is called roots, and this will give you a number of numerical finding methods as well as roots for quadratic, cubic, quartic equations. So up to the fourth polynomial. So you can do that. You go online, check it out. We might deal with this later, but for now, I think I'm gonna do it manually. Okay, if you're not interested in the manual implementation, just skip the video. Okay, but this is what I'm going to do, so just so that you can go through it. So what do we have with a cubic equation formula? Okay, what do we have a cubic equation formula? Well, let's see. Let's see. Okay, for now, before I start, I want to save this to a Git first. Okay, before I do anything. Remember, I like to save a lot. So I'll just add this to Git because okay, so I'll just add this to Git. I'll mark the Ping Robinson eos.rs file for saving. What I want to do is I will say, yeah, because I want to save the progress, right? So I added coefficients for cubic polynomial. Now this is not the best commit message, but I think for now we'll just live with it. And I'll sync the changes by pushing it onto GitHub. Okay, and that's done. So no git push, no nothing. Okay, if I reload, you can see that there's the added coefficients for cubic polynomial here. So we had some changes and we added this bunch of code here. So all that is good. It's now saved on the cloud. Okay, so this is a regular good saving habit. For if you are the only person managing the repository, this method's okay. Otherwise, you got to learn something called branching with Git. But I'm not gonna go through that. That's not the point of this series, so I'm just not gonna do that. Keep it simple. Okay, next thing we need to do is to figure out how to solve cubic polynomials. Okay, and for Ping Robinson equation of state, we only want to concern ourselves with the real roots. The imaginary roots are really not a problem, because imaginary volumes are not the, yeah, they have no physical meaning or no physical sense. Okay, if there's a complex volume, so to speak, it doesn't have any physical meaning. Usually what happens if there's only one root, it means that you are probably in a supercritical regime, okay, where there's only one single phase and this becomes a supercritical fluid. Okay, so we don't need to deal with that. Okay, I hope you know what supercritical fluid is. It's basically a fluid that's above the critical temperature and pressure. So that's what this critical temperature and pressure here is. When it's over the critical temperature and pressure, it will start behaving, well, the liquid and gas phase becomes indistinguishable. So it will behave as if it's only one phase. So you'll have a liquid-like density, but you can compress it like a gas. Somewhat. Yeah. So or rather the liquid and vapor phases. Correction. Liquid and vapor phases become almost indistinguishable. So basically it becomes a single phase, so to speak. So we like to call this, I think, gas. So this gas, the difference between gas and vapor is that, at the temperature and pressure, you'll be able to find one phase only for gas, but two phases if it's a vapor, because the vapor is usually in equilibrium with the liquid. So anyway, that's the thermodynamics of it. I will skip that. I will not go too much into that. Yeah. So what is next? Yes, we need to figure out how to solve cubic polynomials. So from a programming standpoint, well, there are two ways we can do this if we want to put this in manually. Okay, excluding, and we for now exclude the option that we want to use a package or we want to import a crate. So what we want to do for now, is based on this formula given to us. I got this from Paris Chemical Engineering Handbook. You can get it from a lot of resources online. So I cite this Paris formula. Okay, so I got it from Paris Chemical Engineering Handbook. So we need to do all these following steps. We need to calculate a term R, get a P and Q, and then go all the way down, solving all of this. And of course, we have to figure out what kind of unit this is. We have no idea, okay, what this unit is. Okay, whether the things in here, should it be a radian or should it be degrees? Okay, we still don't know. So, well, we have to figure that out. No, I have a strong suspicion it's a degrees because we have 360 degrees and k equals to 0, 1, and 2, right? So 360 degrees, you kind of divide it by 3 so that you sort of have 3 equally spaced roots. That is my guess. I could be wrong, but we'll have to test it out. Okay, so these are the things to do, and if you can imagine with me for a while, based on what we have already done, just coding 5 formulas, that's about 40 lines of code. Okay, you can imagine how many lines of code this will be. So if we want to use this for we want to try this formula, we can code it here. That's the first way. I was saying we have two ways. We can code it here. All right, we can code it here. Or we can code it in a separate function. Okay, my preference is you code it in a separate function so that you can test it. Okay, you can test it straight away whether the root finding algorithm is correct. Okay, so I'm going to make a new Rust file. Okay, I'm going to make a new Rust file. Where can I? Yes. Yeah. I'll call this cubic roots.rs. Okay, cubic roots.rs. Okay, I will of course put it over here. And okay, why am I using the mouse? Oh yeah, I have to click here. Ugh. Okay, I'm gonna do a mod cubic roots. Okay, I'm gonna run into problems. Oh, okay, it should not be here. Okay, let me see whether let's create. Oh, right. Create module at Ping Robinson EOS cubic roots.rs. Well, I don't want to make it under the Ping Robinson. You can use it anywhere. So never mind. I'll delete this because if you put a module, if you make a module under the Ping Robinson EOS.rs and you try to import it from there, it has to be under the PREOS folder. So I don't want it to be like that. So instead of that, I'll just put the cubic roots rs over here. Okay, mod cubic roots. Okay, and that's how I will find my. That's where we will start doing our cubic roots equation. Okay, what's the basic structure of the cubic roots equation? Well, I'm gonna make it a pub function. Okay, find cubic roots. Okay, and this is how we're gonna start. Okay, so for the equation, we need it in the form x cubed plus bx squared plus cx plus d. Okay, so there are a few things here. Okay, all of these are going to be in the float, I believe. Yeah, I'm going to put this in floating point number. So B is going to be F64. C is going to be F64. D is going to be F64. So that's B, C, and D. All right, so make sure this is a public function so that you can use this elsewhere. All right. So next thing, after we have B, C, and D, we're going to need to find R. R is dependent on P and Q. So R is going to be a F64. R equals to P divided by 3 cube plus Q divided by 2 squared. So I'm just going to blindly, so-called, just copy all these formulas down. Let R, this will be F64, of course. Okay. P and Q are also F64. Okay, so all of these are float 64s. So what is P? P is 3C minus B squared over 3. P equals to 3C minus B squared divided by 3. Okay, so I'm just going to do that. P equals to 3.0 times C minus B square. Oh, there's no. Okay, power F 2.0. Okay, when you're float, you can just raise it to the power of anything you want. That's pretty okay, not so bad. And then what I'll do is I'll divide by 3.0. Okay, that is my P. Okay, so that's P. I'm going to do something similar for Q. Q equals what? 27D. 27D minus 9BC plus 2B cubed divided by 27. Okay, so I'm going to just do that straight away. Q equals to 27.0 times D minus 9 times B times C plus 2 times B power F. Okay, just power, raising it to a power. So this is the power of 3, and then I'll do by 27.0. With float numbers, you can do the power F much easier than in the units of measure thing. Okay, and we are running into errors now because I forgot to mention that this should be floating point numbers, not integers. So I need to put a 0.0 here, or the other way is to put the F64 right here. This will designate to us that that the 9 and the 2 and the 27, either you put a 0.0 or you put a F64 over there. Okay, that will tell Rust that, hey, the Rust compiler that, hey, these are floating point numbers. Okay, so now that we have P and Q, we can actually find R. Okay, R equals to P divided by 3. P divided by 3.0. Okay, power F 3.0 plus Q divided by 2.0 power F 2.0. Okay, so that's how you do raising stuff to the power using floating point values. Okay, so that is finding R so far. Okay, that's finding R so far. So once we have R, we start having multiple cases. Okay, so if what we do next depends on R. Okay, if R less than 0, we have 3 real roots. Okay, so let's do an if statement. Okay, so I don't know whether I introduced if statements before, but this is how you do if statements. If R less than 0.0, then you have this you open and close a curly brace, and this is how you do your if statement. Okay, that's how you do your if statement in Rust. So if, okay, this is a boolean, called boolean, which is a true or false value. So this allows us to evaluate whether R is less than 0. So that's how we're going to do it. So if R less than 0, we are going to execute a bit of code. If it's somewhere more than 0 or equal to 0, then it's gonna be another case. So let's see. All right, so let's just go through with it. Okay, if r is more than 0, expect complex roots and one real root. If where is this? Okay, let's see. R more than 0, expect complex roots. Where's the r is less than 0, 3 real roots? I believe there's a r equals 0. Okay, r equals 0, expect 3 real roots, both are equal. So there are 3 cases, right? One is r less than 0. Here is where we expect 3 real roots. Okay, r is equal to 0. So I'm going to do else if. Okay, else if. That means I'm checking for the second condition. R equals to 0. The way we check using whether something is equal, you have to use 2 equal signs here, because the compiler in Rust understands this equal sign, that meaning to say that I want to assign the value of r. For example, the value of r is equals to the value of all the terms over here. So equal is an assignment operator, but if you use double equal, this is comparison. So you're checking if these two are equal. So okay, so first thing first, the code here checks if r is less than 0. If it's not less than 0, it checks if r is equal to 0. If it's not equals to 0, then it checks if r is more than 0, which is basically every other case. So what you can do is 2 ways. Else if r is more than 0.0, you'll execute some bit of code, but this is not necessary. So what you can do is, this is not necessary because this one covers all the real numbers less than 0. This one covers the case where r is equal to 0. This code block here will cover all the cases that are more than 0. But since these 3 cases here represent the entire set of real numbers, okay, I don't need to check again if r is more than 0, because if I check that r is not less than 0 and r is not 0, then r has to be more than 0. So I can actually delete this thing here, and okay, we will have this if else statement. Okay, this is an if else statement in Rust. So if r is less than 0, do some code. Else if r is equal to 0, do some code. And if r does not satisfy either of these 2 criteria, then we execute the third set of codes. So this is expect 3 real roots, 2 of which are equal. Okay, and what's the last one? Expect 1 real root, 2 complex roots, which are conjugates of each other. And that's good. That's what we should expect. Okay, so there are multiple cases we can find in each of these cases, right? So this is we can execute code, for each of these cases, which are slightly different. So this is how we can do, the if-else statement in Rust. Okay, so this is the case where r is more than 0. Okay. Okay, so what do we do here? Okay, so for r more than 0, right? R less than 0, r less than 0, we will have this formula thing here. Xk equals to yk minus b over 3, where yk is this very, very long thing. This is where the cosine comes in. And then we have a phi over here, which is cosine inverse of this thing here. And then we have again multiple cases where q less than 0 or q more than 0. Okay, so right. So let's check it out here. Q q less than 0 and q more than 0. Okay, so okay, let me check. Okay. So first thing first, we need to find this yk value. Yeah, what's yk value? In these two cases. So q more than 0 and q less than 0. However, this unfortunately does not cover the q equals to 0 case. So we'll need to deal with that separately as well. So if q more than 0, execute some code. Else if q less than 0.0, execute some other code. Okay, else execute some other code. This is the third case is of course the q equals to 0 case. So we'll deal with that at the last part. So we want to get the easy parts out of the way first. Okay, so first thing first, I'm going to declare a variable called yk, and this should be a float variable. Yk f64. This is what I'm going to do. Okay, so yk is a f64 value, and of course xk is a x64 value. All right. So what are we going to do? Yk equals to plus minus of this, where k equals 0, 1, and 2. It's fine. We'll start dealing with that later. Okay, we'll have a phi that we need to calculate either way. Okay, we have a phi that we need to calculate either way. So let's calculate the value of phi first. Okay, let phi there's a f64 also. Okay, so we need to calculate the arc cosine of this term. So q squared over 4, q squared over 4. So so this part I'm going to do it like this. Okay, let phi equals to something. Okay, I'm going to instead of writing one long equation here, I'm going to write a code block. This is just a stylistic choice. You don't have to do it like that, but this is what I like to do. Okay. Maybe I'm introducing too much new information at once. Never mind, forget it. I will not do the code block way. I'll just do it the normal way. Okay, so let's do the numerator first. Let q square by 4. Okay, f64. So this is the numerator. Okay, this is the numerator. So where's q power f 2.0 times 0.25. That's basically dividing it by 4. And let denominator minus p cubed by 27. Okay, this will be a float 64 value. So it's a minus p dot power f 3.0 divided by 27.0. That's the denominator. So let's just check the code. Q squared by 4 is q to the power of 2.0 divided by 4, or times 0.25. Next is minus p cubed divided by 27. So minus p to the power of 3 divided by 27. So all this looks good so far. So let's calculate phi. Phi equals to arc cosine, or rather let's do the numerator and denominator first. So it's q squared by 4 divided by minus p cubed by 27 arc cosine, a cos. Okay, a cos. So this is how you do the cosine inverse. Okay, arc cosine, a cos. So this will get you phi. Okay, we'll need to check whether this works. Okay, so it computes the arc cosine of a number. Return value is in radians. So note that, I'll just write in the comments, note that phi is in radians. Okay, Phi is in radians. So I'm not sure what unit this is, but it really looks to me as if this is a degree. Yeah, this really looks to me like a degree because I'm strongly suspicious because of this number 120. So let me try first, okay? I'm going to bind a new value called phi in degrees equals to 180.0 divided by the pi. Okay, if you want to use pi, you can use the standard F64 constants pi. This number is good. Okay, phi in degrees, 180 over pi, if I'm not wrong, yeah, times phi. So okay, let me just quickly do this. Quick fix, import pi. Oops, sorry. Let me do this again. Quick fix, import pi, import it as a float 64. Okay, so this is one way you can do it. Right, you can use the F64 constant pi, or you can use the UOM to do the legwork for you. Okay, this is from memory that I think radians and degrees is 180 over pi. That's the number. I could be wrong, but I think is that I need to Google it because my memory is just failing me now. Radians to degree. Okay, yeah, 180 over pi. Okay, so well, my memory is not that bad. Okay, so so this is the formula which is correct. Okay, so yeah, this should work, but well, if I'm going to use ULM to do the hard work for me, I'm going to make a new angle. I'm going to make a new angle unit. Okay, I'm going to, of course, import more than angle. I'm going to import everything. Okay, anyway, anytime I use this star sign, again, this is a wildcard, meaning you say anything under the F64, I'm going to import all the modules there, not just the angle. So that should be okay. Okay, angle, new radian. So angle, new radian, phi. Okay. Okay, so this is going to be phi. Phi dimension. Okay, let phi degree equals to, so this one is to get UM to do the unit conversion for you. Okay, phi dimension get degree, and that's it. Then I'm going to do a quick fix. Oops, press the wrong button there. Cubic roots.eos. Yeah, let's see what's the thing. Yeah, UMSI angle degree. I can of course do the quick fix import. That's fine. This is my phi in degrees, and I got UOM to do the hard work of conversion for me. So this is phi in degrees. This is a F64 by default because the UOM package we use is a F64. There can be F32 as well, but for now we do F64. Okay, so phi degrees is as such. Phi degrees is here. So that's fine. I have my phi in degrees. So yeah, let me just continue. Okay, let's see. So we come to the first case. Okay. Oh, this is if R is equal to 0. Okay. Actually, I'm gonna copy all this here, paste it here also, because either if R equals to 0 or R is less than 0, we basically are running the same code. Okay, so we have a calculated phi in degrees and radians, so we can use both if you want. Okay. Next thing is to check if Q is equal to 0 or less than 0 or more than 0. So all of this the if else structure, I need to put it here as well. We'll deal with the case where these are equal later on. Okay, we'll deal with the case that these are equal later on. Okay, so what do we have here? Okay, if q is more than 0, this is the formula to use. So q more than 0, yk equals to minus 2.0 times, what is this? Minus p over 3, and then you have to square root the thing. Minus p divided by 3.0 square root. This is what it looks like. Okay, we are going to run into errors, I believe. Okay, and then you need to cosine 5 by 3 and 120 times k. Okay. Now the thing over here is that 120 times k is a little bit how do you say this? K has not been determined yet. So there are actually 3 values of y. There's y1, y2, and y3. Okay, so this is going to be like so-called, this formula is so-called going to be repeated 3 times. So rather than getting yk, over here, I can actually define a function, right? So function, I can define a function within a function. So that makes it a bit easier, so that I can call the same bit of code again. Okay, again, why am I doing this? It's because I will need to use this formula again and again. So k equals to 0, 1, and 2, meaning to say I'll need to use this formula here 3 times. Okay, I'll need to use the same formula here 3 times. If I'm going to use it 3 times, I'd rather code it into a function so that I can do something about it. I mean, I don't have to keep typing out the same code over and over again. So let me just write a function here. Okay. So I'm going to call this function get yk. Okay, so there are 2 parameters here. So one is k, which is a u size. Okay, this is 1, 2, or 3. So 1, 2, or 3. Okay, get yk. And what's the other thing we need to supply? We need to supply p, which is an f64, and then we need to supply phi, which is also an f64. Okay, I do not know whether it's degrees or radians, so we'll just leave it for now. Okay, the return type is a f64, and then I'll close it like that. So this is how I'm going to do it. Okay, the compiler will give me problems because it will give me problems because I am not able to I'm not returning anything yet. So what I need to do is to put this here, these two bits of things here, and I will not have yk outside anymore. Okay, I will put this over here, yk equals to, okay, I'll put it within the context of this function, and then I'll call the function here multiple times. All right, I'll call the function here multiple times. So let's see. Okay, there's a few things we need to do. Okay, a -2 here, minus p over 3.0, which is here. We square root the whole thing, and then a cosine of 5 by 3 times 120 k. So the last one over here, is phi divided by 3.0 plus 120.0 times k. Okay, this is going to be a problem because we normally cannot find integer. We cannot multiply integer by a u size. Okay, u size is a unsigned integer. This is an unsigned integer, meaning to say there's no minus over here. And true enough, we can use this to represent k because k is not negative, so we can use unsigned integers. Okay, so 120 times k cannot be used, so I need to use convert this to an f64. So I'll put a k as f64 over here. Okay, so this is how I convert my u size into a k. because it's pretty easy to do so. It's a primitive conversion. And to shorten this code, I will just delete this line. I'll just want the yk equals to all of this formula over here. Okay, and I think I forgot one more step. Okay, I have a minus 2.0. I want to square root, no, minus 2.0 in front. Okay, square root of minus p over 3. Okay, square root of minus p over 3. I only hope that p is negative. It could be negative, it could be positive, but I just hope it's negative. And since we have 3 real roots, if we have 3 real roots where r is less than 0, then we should expect p to be negative. Okay, so you see, if r is less than 0, what happens? We have a positive number here because q is real number. Q is a real number, and whether it's positive or negative, it will be more than 0. If r is less than 0, then the only thing that ensures that r is less than 0 is this p over 3 cubed term. If p over 3 cubed is less than 0, that is a necessary condition that will at least sort of make this r is less than 0 case possible. It's not sufficient, but it's necessary. So we call it necessary but not sufficient. Yeah, so if r is less than 0, then definitely the negative term will be p. So p is actually negative. That's why we have a minus p here. So that's fine. We don't have imaginary number problems. Now let us return yk. Let us return yk. Yk right here. All right. And of course, xk as well. Xk, we can actually code a function called getXk, because we'll be getting yk as xk and yk. So get xk, what I need to do is xk, which is f60. No, this is not right. Xk is based on yk. So yk is a f64 value. Alright, yk is a f64 value, and I want the b value, which is also an f64. And then I'll just return a f64. Okay, so that's fine. And xk is very simple. That xk equals to yk minus b divided by 3.0, return xk. Okay, so that's all good. We have a function to get xk and yk, and then this one becomes redundant. So we'll just get rid of it. So we have a function to get yk and xk. All right. Now, again, yk, it really depends on the sign of q. So I'm going to bring all of this into the function. So again, I don't have the if-else statement that I need to repeat all the time. So so not only does yk need let me try and equalize all of this. Okay, that's not really working. I want to tap like that. Yeah. Okay, so yk actually needs a q value as well. So let me go and put a q value. Q f64. Yeah, the indentation is just weird here. I don't know why. Okay, but anyway, so yk is as such. Okay, yk is as such. K use size p f64 phi and q. So yk really depends on the sign of q. So if q is less than 0, we indeed have this thing. Okay, so I'm going to do a let yk here. And now I'm going to paste this at the q more than 0 case. Okay, q more than 0 case. And this is what I'm going to do. So basically, I'm defining yk over here. And then based on the case that yk equals to some some funny values. Yeah, yk equals to some funny values, then I'm not going to return it. I mean, it will depend on the formula, right? It will depend on the formula. I mean, it will depend on the formula will depend on the value of q. Maybe I'm doing this for too long and I need a break. But let me just finish these two first. Okay, let me finish these 2 bits first. Then I'll just call it a day for this video. Okay, q more than 0, then we have yk goes to minus 2 square root minus p over 3 5 by 3 plus 120k. So that's 1. This one is yk equals to 2. This is the plus version. Plus 2 minus p over 3 cosine 5 by 3 plus 120k. Okay, so let's just copy and paste this here. And then what I'll do is I will take out the minus, and this is the q less than 0 case. Now, where q equals to 0, we have not quite figured that out. So maybe we'll just leave it here as a to-do. We'll deal with this later. Okay, q equals to 0.0 case for root finding, a cubic root finding, not done yet. Maybe we'll do it next time. So yeah. Okay, this is for now. I'll leave the video here, and I will just add these two and commit to Git. And what will it be? Okay, implemented 3 rail roots partially. Okay, I will commit this and I'll sync the changes. Okay, so that's all for this video. I'll see you next time.